different meters, and I even talked to Ross today about a meter. So I just want to go over a couple of more meters that you may run into or may have, or let me give you some other things that you can use for testing. So I went on YouTube and got a few more videos of different meters that we haven't talked about, and there's just so many different tools and meters out there that you guys can use to test appliances. This one is a video from Klein themselves, who make the meter, and they're talking about testing frequency. So let's take a look at this video for a minute. It's only 2 minutes long. No.
Hi, I'm Bruce, and today I'd like to talk about some of the more advanced features that you'll find on some of our multimeters and Klein meters. Measuring frequency does exactly what it says. It measures the frequency of a AC signal. What comes out of your outlet in the United States is 120 volts at 60 hertz. If you were to plug this meter into any standard outlet in your home, you're pretty much always going to see 60 hertz coming out of that. But where you might not always see 60 hertz is something like a battery backup system. And so measuring the frequency and voltage coming out of the battery backup could be a very useful thing. So let's turn this guy on. As you can see, he's not plugged into anything. But if I measure what's coming out of this jack, let's measure voltage first. And I have 100.
Now if you guys look at, he's on voltage, but if you look right up here where I have the mouse pointer at, it's got a wavy line. That wavy line is an indicator of alternating current, or AC voltage. The next voltage scale up here, the video doesn't show too well. We'll have a solid and a dashed line. That's for DC voltage. So I know the video says he's checking frequency, but the first thing he's doing is checking the power output of this battery backup system. This is something that you would have like if in your office or at home connected to your computer, and if the power was to go out, this has a set of batteries in it that will allow the computer to stay on for a little bit of time without having FP&L powered up, or your local power company. But now he's going to go into frequency, and then I want to talk about that for a minute.
119 volts coming out of this battery backup. Remove this lead when I switch over to the frequency position. Stick it in. And I'm measuring 60 hertz. People that are doing bench work can use this to measure much higher frequencies than 60 hertz. This would relate to people that are doing actual design or development work, maybe some audio work. As you can see, I can change my frequency here with this frequency generator, and 171.6 on the meter. So it's just literally measuring the frequency of the signal that's being put into it.
Okay, so why would frequency tester be important, and where would you use it in an appliance? We talked about that the other day. Anybody got an answer? No? Okay, well, we discussed that on these variable capacity compressors on refrigerators, those compressors have a computer board connected to them, and these compressors run at variable speeds. They don't always stay at the same speed. So on these variable speed compressors, how does the compressor know what speed to run? So the main control board of the refrigerator talks to what we call the inverter board, which is that little board that's connected to a compressor, and it tells the inverter board, okay, make the compressor run full speed, make the compressor run half speed, make it run slow speed. And the main board actually has two wires that go from it to the inverter board, and those two wires have variable voltages. On the Electrolux one, it's both AC voltage, DC voltage, and a frequency. And we're not talking about 120 volts because the inverter has a separate plug of two wires, which is 120 volts coming from the wall. They always go to the inverter at all times. But the communication cable between the two boards is what we call it. It's going to have a low DC volts, a low AC volts, And the frequency is one of the more important things. That frequency is a signal from the two boards telling the compressor what speed to run. Well, what am I talking about when I'm talking about frequency? Let's use the beach as an example. When you're sitting at the beach early in the morning, if you've ever gone to the beach at different times of the day, usually there's not much wind or not much heat in the day, and you got these small waves coming and hitting the beach, and then that small wave returns back to the ocean. And how fast or how many times per minute that wave hits the beach and then returns is frequency. You could say, oh, it hits the beach 30 times a minute, or it hits the beach 5 times a minute. That's frequency. It's how many times a minute. But there's other changes to the frequency, because not only can it come to the beach more often and return, and come to the beach more often and return, but on a real windy day, that wave might be 2 or 3 times higher than it would be on a very low day. So the frequency you were talking about is not just how many times does it hit the beach and return, but how many times does it hit the beach and return, and how high is that wave of water hitting the beach. So we talk about that in the way of electricity. Electrical current goes backwards and forwards in a circuit, and how high that wave of current is, or the stronger that wave is, that's the frequency. So when you're looking at the meter, and I went back to this video and I pointed out that wavy line here on the signal, that's almost like the beach wave that I'm talking about. So that's what they're talking about when they're measuring frequency. Why is that important? Well, let's say your compressor's working or not working at all on a VCC refrigerator. How do you know if the compressor's good? How do you know if the inverter is telling the compressor? Or how do you know the main board is telling the inverter board to tell the compressor? So one of the things we want to do is we want to see if we got those voltages from the two boards, AC and DC. And then we also want to check the frequency and make sure that the frequency is the right frequency. On some refrigerators, 255 is the maximum speed on the frequency. So that's one of the tools that you're going to use. Do I use it often, or would you use it often? No, but we go back to this, $35, $40 Klein meter. We talked about it can do capacitors. It can check some diodes, not real high ones, but they showed you how to check a diode using a 9-volt battery attached to it. And now it can do frequency. It can do DC voltage, it can do AC voltage, and it can do ohms. So for an inexpensive $35, $40 meter, you can actually get a pretty decent tool to do all the different type of tests that you want it to do. Do any of you have any questions about that frequency and testing frequency?
Could frequency also be used to measure the pressure switch when a washer is filling with water on certain models?
Oh yes, you're very correct. I think the GE washer, which is also similar to the LG washer, the water level switch on some of those units are not a pressure switch, they are a pressure sensor. And based on the frequency is how full it is. Now I know in some of the diagnostics of those machines, the diagnostics will measure the frequency as it's filling with water to show you that the pressure switch is working. But yes, you could use this meter to also measure the frequency off that water level switch. And if you're not having the right amount of water, or you're having the board give you an error as a pressure sensor error, how do you know it's the board or the pressure switch? You could use this same frequency setting on this meter to do that test. So that was a good question. Anybody else? No? Okay, so here I have a fluke meter, and this is Ross's favorite. And they want to talk about measuring frequency with a fluke meter. And I want you to take a look, because they do a little more explanation of frequency.
Fluke multimeters include a lot of advanced measurement capabilities that can enhance your troubleshooting style. On the Fluke 87.5, in addition to your standard measurements, we also have some more advanced measurements up along the top here. The one we're going to be discussing now is the frequency and duty cycle. So to how to measure frequency, I have a 110 volt signal I simply hit the Hertz button, and now I'm measuring the frequency. As a quick review, what frequency is how fast is this signal moving. And with the sine wave, we have a power company that's generating a circle. And then we take that circle and we send it down to us. If the circle only went in one direction, it wouldn't get anywhere. So it kind of sends this way and this way and this way. So it's cycles per second. In the US, it's 60 hertz. In the EU, it's 50 hertz. And if you're working on airlines, it's 400 hertz. And this is an indication of how fast it's spinning. Now, as you get more into working with motor drives, this measurement becomes a little bit more complex, because the motor drive takes your normal sine wave and puts it into a pulse width modulated, or a PWM signal. A normal multimeter is not going to be able to measure this frequency properly. We added a feature on the Fluke 87.5 and our 1587. If you see next to the AC volts, there's a low pass. By hitting this yellow button, what I've done is I've now converted this into a special measurement mode that will measure this pulse width modulated signal accurately, giving you the frequency. So you can see if the motor is truly at full speed at 60 hertz, half speed at 30 hertz, quarter speed at 15 hertz. So that's a useful addition that we put into all our new Fluke 87 multimeters with the hertz and the duty cycle function. If I press this button one more time, I go into duty cycle. What duty cycle is the percent on versus the percent off. And this can help you troubleshoot power quality problems. If I have a good circle that my percent on and my percent off, or low, negative, is going to be equal. It's symmetrical. If I have a bad signal with a lot of harmonics, I will only see 20 to 30% on, and then the indication at 20% on is 80% off. So by simply doing the duty cycle measurement, I can see if the waveform is symmetrical.
Wow, I'm not even going to play that video any longer, because I'm sure a few of you are like listening to this guy and you're like, what the heck is he? Yeah, but this guy's speaking another language. Okay, so basically, when they create this sine wave or this cycle, just imagine a magnet. Let me just go to my drawing tool here and try to give you just a little brief explanation of what the heck is this guy talking about. And what happens in a meter is, first of all, we have a coil of wire, okay? And then I'm going to draw this over here as a separate piece because I want to be able to do something with it. But here is a magnet. You got a north pole and a south pole of a magnet. And the difference of those two poles, and I'm going to be honest with you, I don't know which way they flow, but there's a magnetic field around the outside of this magnet. And I'm going to say that this goes clockwise, this magnetic field here, okay? Now the south pole also floats around the outside of that bar magnet, and I'm going to say that this one is going counterclockwise. And that's the way the magnetic field is facing. So, oops, let me just undo that. Well, never mind, I'll just erase it. I love my tool. Still got to learn how to use it. So let's take this tool here, and let's move this magnet. Let's move this magnet closer to my coil of wire. Now, in order to explain this thing properly, let's draw that line that the guy was showing you on the video. That you have a line here that represents voltage. So the line itself is 0 volts. And you say, well, what are you talking about, 0 volts and so forth? Well, when you put the magnet next to the coil of wire, there's a little electrons and atoms that are inside this wire, and the magnetic field is trying to have all those electrons that are in the wire itself to line up and go in one direction. So if I was to take this magnetic field, and let me go back to my meter so I can do with my mouse. If I take this magnetic field and I start to rotate this magnetic field this direction and move it 90 degrees, now what happens is, and I'm going to move it a little bit away so I don't mess up my coil, what happens is the magnetic field all these lines of flux, they call it, are moving the electrons in this wire. And which way are the arrows pointing? Up or down right now? Anybody?
Down.
Yeah, they're pointing down. So basically what is happening is the electrons, because of the magnetic field, if I can get my my drawing tool to work here, the electrons are being forced in this direction by the magnetic field. So I'm just going to draw this, let's just say downward. I am pushing the electrons in that wire, and I've gone from this point here to this point here. Let's call this point A. Point A is right here. Now that I rotate it, right now this magnet is at point B, right? And so point B would be right here at this magnetic field. So when I move one electron in this wire here, and I'm going to put a light bulb on the other end just to give you something to visualize. When I move that magnetic field, I'm pushing all the electrons here, and when one electron moves, it's almost like you're all standing in a hallway and it's only wide enough for one person. So if one person moves, everybody moves. So in this circuit, when I move one electron, then this whole circuit, all the electrons move one pace. If I got a real strong magnetic field and I got a coil of wire, instead of moving one electron, I'm moving all the electrons in this coil at the same time. So I can be moving hundreds and thousands of electrons here, but I have a single wire here. So now I'm creating an electrical pressure. In other words, I'm trying to move more electrons here than this single wire can handle. That's how we're creating that voltage pressure, the electrical pressure. And when the magnet is right here at point B, I'm at the maximum pressure in one direction. So this sine wave here is basically measuring the spinning of this magnet. Let's go a little bit farther here. And now that I did this, now I'm going to rotate this magnet another 90 degrees. So now the magnet is as far away as it could be again from this coil, and I'm going to move it down just a little bit. And instead of point B now, where point B was here, for example, now I'm at point C. So what happened now is that as I started to go away from the coil, the magnetic field's getting weaker and weaker. I'm not moving as many electrons. The voltage drops back to 0 because I'm so far away I can't move the electrons here. Okay, so now I'm at point C, which would be right here on the scale. So now what happens? Well, I'm going to grab my magnet again, and I'm going to spin it another 90 degrees, which is in this position here. And let me get it away from that point B for a second. Now I'm as close to the coil of wire as I was in point B, or step B, but instead of the magnetic field pushing the electrons downward, it's pushing them which way? Look at the arrows in the south pole. Are they going down or up here?
Up.
They're going up, which is correct. Oops, somehow I messed up and moved this. They're going up, so I'm actually going the opposite direction. Instead of going down now I'm pushing the electrons the other way through the circuit. And therefore, as I got to the maximum upward, which would be D. So now this is pushing them to maximum voltage here. So the next step would be to bring this magnet full circle and come all the way back up to here, and then I drop voltage again. So at this point, let me get my drawing tool here. At this point, I'm back to 0 again, and then we go backwards and forward. And if you could see, that is that sine wave that they're talking about. The faster I spin this, the closer these pulses will get. So if I was spinning it on a regular household circuit, that was 60 hertz cycle. That's 60 upward pulses, 60 downward pulses. So I'm just going to go like this many times. So if I have 60 up and 60 down, how many total pulses do I have? 120. I have 120 total pulses. Every time I have a maximum pulse, I have the maximum voltage. Every time I'm at this line, I have 0 volts. So your eye cannot register it, but the light bulb in your house, the regular light bulb like this light bulb, actually turns on and off 120 times a second or 60 times a second, depending on the frequency. Have you ever taken a pen or a pencil and waved it in front of a TV and saw those lines on the TV with your pen or pencil? Well, what that is that your TV, when it's on and off, it turns on and off so many times a second, your eyes don't see it. But when you put the pencil over it, it separates it. If you ever watch movies that were not that professionally done or showing cheaper TVs, like the old black and white TVs, you might notice that they have a TV in the background and there's some line on the TV. And what happens is that TV is turning on and off so many times a second, and when your camera is videotaping it, if you've ever seen a reel of film, it's just like a bunch of little pictures. So every little picture is on, and in between the next picture, there's a little black line. So that picture is turning on and off so many times, and the next picture is just a slight change in movement. So when you see that on a TV in a video or something, what happens is the frequency that the camera's on is not the frequency that the TV's on. So they're pulsing on and off at different frequencies. So the camera is so fast, it's picking the offward frequency. And you're like, well, what do you mean it's on different frequencies? Well, in your house you have line 1 and neutral is 120 volts. But you also have line 2 and neutral, which is 120 volts. Well, how does line 1 and line 2 together make 240? Well, each one of them are a different frequency, and in order to do that, what they do is they have a different coil of wire somewhere else. And I'm just going to put one here for an example. Now, if I take that magnet that we've been using and I rotate that magnet, oops, not that one, I rotate the magnet this way, the coil on the left, which way is the frequency going, up or down? On this side here, on this one here, and I'm just going to use my marker here, the current is going downward, correct. But on this one here, this current is also going down. So they're actually opposite each other, because if I rotate the magnet, wait a minute, I did something wrong here. But the frequencies are different. It's hard for me to explain. Let me change what I said, because I know I made a mistake here. I'm going to move this magnet. I'm going to put that coil of wire here. This will make more sense. So, yeah, it's downward, but it's not downward like you see in this sine wave, so I have to redraw it so you can see it better. So if the magnet's here, it's pushing this one, and I'm going to call this number 1, and this one number 2. So on coil number 1, I have maximum voltage. So I'm at this point, maximum voltage on coil number 1. So this is number 1. Well, on coil number 2, do I have any voltage being created at this point by this magnet? No, I have 0 volts, because 0 volts, the coil's as far as away it can be from this magnet. So at number 2, I have 0 volts being created. So if I was going to take this magnet and rotate it, if I was going to rotate this magnet like this, now coil number 1 is at 0, which is point C, and coil number 2 is at maximum voltage. So it's the same direction this one is. So at this point, I'm at maximum voltage here for number 2, and number 1 is here. So look at the difference between these two. This is what we call potential difference. So one is at 0 volts and the other one's at maximum 120 volts. So if in the power company they put multiple coils all the way around, even if you have a generator at home, they have coils that all the way around. So as they spin the magnet, not just one coil of wire is picking up the current, but all the coils are picking up, and they're all different phases from each other. Normally in a house we have what we call 3-phase, which actually has, well, not in a house but in commercial, is we have 243 phase, and we can even go as high as 480, and that's dependent on the amount of coil wire we have here in the magnetic strength. But we have a line 3 here. So what makes difference between line 1, line 2, and line 3 is that one here is at 0 volts. This one's at maximum volts, what we call negative volts, and I'm just going to write negative. And then we got a third one that's up here, which is over here, for example, which is a positive volt. So now these two are as far away as possible. Now we have 240 volt potential between these two. Remember, they're turning on and off so many times that you're saying, oh, well, this one's at 0 and this one's at here, it's only 120. But their frequency pulses are so far apart that there's always going to be 240 volts on 2 of these frequencies at any given time. And I know it's a little confusing, but when we're talking frequency, we're measuring how many times does this magnet pass this coil of wire. And we can use computer boards to generate frequencies, and we can use it to control water level like we talked about, or the speed of a compressor. And using that hertz setting on a meter is how you're going to do it. So what this guy's explaining here is that magnet that's spinning around, and that's just a single coil of wire that's being measured, or one line. When we get into the square block, this is done through electronics, and they call it pulsated modulation, where we can pulse them faster or slower, or pulse these higher or lower, so we can convert this to this, and we can control a motor speed or a motor frequency. We get into frequency drive systems. It's not going to be much in appliance repair. They're more in commercial application, but using that scale is how you would know whether your control or your motor is working properly. So I'm not going to get too deep into it. I got way far off of what I wanted to talk about with my meters. But Samurai, the appliance guy, he's got a lot of good videos and stuff. So let me just go to here.
The lights that indicate whether you got a bad.
And I want to get into a different meter. Last weekend I was at a hotel, and the dryer was taking 2 or 3 loads to dry. And when the maintenance guy came, I was trying to explain to him, he's opening up the machine and he's testing thermostats. I told the guy, I said, listen, it's getting hot. It's just taking too many loads to dry. Most likely the vent is blocked, or the hose in the back of the machine's blocked. And the guy at first, was like, yeah, whatever. And I'm sure if any of you ever gone to fix something, the customer always knows more than you. So, you have to take it for granted. But this is a special meter that you use to test to see if the dryer is venting properly. Now, in the Whirlpools, it's easy to test right through this filter here. But let's take a look at this meter that they're demonstrating here.
Dryer vent, borderline, mediocre, or good for all dryers. And we're going to demonstrate here in just a minute using this on a real-life service call. So we're going to run the dryer vent back pressure tester on this dryer at the customer's request, even though this looks like and is a UL-approved, AHAM-approved dryer vent. In fact, this is a Whirlpool kit. It's all metal. It's fireproof. Very simple. Comes out with a fixed 90-degree fitting from the back of the dryer up through metal ductwork. This is the Expando type. It's not smooth walled, which would be absolutely ideal, but this is okay. This is acceptable. And it goes out the wall through another 90-degree fitting, and that goes straight out. That's an external wall. So it's very simple.
Now, first of all, before he says anything, to come out of the back of the dryer here, right. Let's see. I'm trying to find where it is in the video. Right there. To come out of the back of the dryer and go straight up and do this long tube and go back down, excess tubing, really smooth wall or whatever, the shorter the length of tube that air has to flow, the less back pressure you're going to have, and the better the dryer is going to vent. If you're going to come out of that 90, which a 90 I was always told is equal to 5 feet of straight pipe, if you're going to come out of this 90, why are you going to go way up in the air and then go back down to a 90 on the wall over here, on this fitting over here? If you could have just rotated that 90 to the left and gone straight into this, you probably could have taken off about 80% of this tube and going from this one, if you just rotate it so it's going to the left and the other one on the back of the dryer goes directly to it, you could run a straight piece of pipe between the two and you would actually make the vent proper. So let's finish watching this test for a minute.
Degree fitting, and that goes straight out. It's an external wall. So it's a very simple dryer vent. The nice thing with this system too is that to pull the dryer out, you disconnect the vent right here, and the whole dryer then can just be pulled out to service behind there if you needed to do that. So the reason we're doing that is even though a vent can look good and appear to be a specification vent and up to spec, it can still be bad in a variety of ways. Lint can still accumulate, particularly in those 90-degree fittings. But an easy way to check it out is to use the dryer vent back pressure tester. And we're going to do that right now. Okay, so we're going to get ready to run the vent airflow tester. First thing you want to do is make sure that your lint filter is reasonably clean. This one, it's got some scuzz on there, but it's reasonably clean because you don't want to produce false results if you're with a dirty lint screen. Wherever your screen is, sometimes they're on the door, sometimes they're up here, you know where your lint filter is. Make sure that's clean before you start. Go into a fluff non-heat cycle, set it for that. Now to start the instrument, press the power button. The power indicator will blink red, and it's going to stabilize here in just a few seconds. There, steady green, that means it's ready to run. Now we put the vent tube in the dryer, and now with the dryer running on a non-heat cycle, the instrument is scanning, and in just a few more seconds it's going to stabilize on the airflow indication for this dryer. It has stabilized on yellow, and I don't know if it shows up in the camera, but yellow means for this instrument is it's good for gas dryers, but it's poor for electric dryers. So electric dryers, this instrument's saying, require a more open and free-flowing vent, less back pressure. So we're going to figure out, this is surprising, given the simplicity of the vent that I was showing you just a moment ago. This is a surprising result. And so we're going to...
Okay, I'm going to stop this for a minute. Couple things you have to be careful when you do is, one right here, let me just show this right here. When he went to put this hose in here, you have to be careful how you put that hose in the door, because if you put that hose in the door and the door crushes that hose, this meter's not going to read the airflow proper. Now, I'm not saying he's misusing the tool, but if he does crush that hose from the door, this meter could read a poor airflow. One thing good about this tester is sometimes you go to a customer's house and they're complaining that the dryer's not drying, and you've checked things out and things seem to check properly, and you're like, well, the meter's working fine. I mean, the dryer's working fine, ma'am. The problem seems to be your vent. You need to have someone come out and clean out your vent. Well, a customer may pay a company to come out and clean it, and then 2 or 3 days later, you're back at the customer's house, and they're saying, listen, I had someone clean it, and it's still not working right. Well, how do you prove to a customer that the problem still is the vent? You can say, well, ma'am, I checked everything on the dryer's working fine. It's got to be your vent. So this meter here could be something you could show the customer, say, well, ma'am, listen, I've tested this, and you see it says it's good for gas dryers, but this electric dryer, and it's saying it works, but it's just not good enough. So something like this would be nice to have for those few customers that say they had someone clean the vent, And does that mean that they cleaned the vent properly or did a good job? You don't know. And this is the only way to prove whether it's the machine or not. So is this a must-have tool? Not necessarily. But is it a good tool to have in certain instances? Yeah, it is. And this is another meter that's out there for you guys. So I'm not going to go any further on this video. I got so many videos. Yes.
A couple of things on that meter, because I brought up that very exact meter to you a few months ago.
Yes, I know you did.
But the hose that you're talking about it being crushed in that door, part of that hose is actually hardened, so it doesn't crush. And that part you got to put against the door, not the soft mesh. So it is designed to be closed on at a certain point.
So how much of the hose actually goes inside the machine?
It's a good amount to go in. Like I said, there's a specific part where it's hardened. It's only like an inch or 2 inch long, and that's the only part that can be crushed by the door or put into the door. So whatever length is left, that's what you have.
Okay, so that's a good point, and I'm glad you brought that up to me, because to be honest with you, in all the years I've serviced appliances, I've never used that meter. I never felt it was necessary for me to have, but I see the value in it after watching this video. But one thing he should have pointed out was when you put that hose in the dryer, there's a certain part that you got to make sure that the door closes on, because you don't want to put it too far in or not far enough in so that it's going to read properly. And like you said, there's a hardened part that keeps that hose from being crushed. So again, accuracy on using your meter, and that's part of this assignment, was using that meter and making sure that that meter checks properly. Now, I have another meter here called a hermetic compressor analyzer. I don't know if we still have this one in school. I forwarded the video to the unit, and this here is like almost a homemade video. But what he does is he connects this device to the compressor. I'm seeing if I can move the video back just a little bit.
Bimetal disc, and when that bimetal disc.
And if you look, he's got the red, the black, and the white plugs are plugged directly to the compressor pins or the windings on here, and then another one is connected to ground. And this meter can check the windings out and see if the windings are good, open, or shorted just by pressing a button. It's an expensive meter where an ohm meter could tell you the same thing. The only nice thing about this tool would be is you could connect it to a device, and it had a very different...
Unbogged, like if this thing was, bogged down or whatever. Let me go 300. I think you gotta hit start again.
Okay, so what that first switch was that he was switching, and I wanted you guys to see that before I talked about, is you got one switch to determine the voltage that's coming in, because you might have a 120 volt compressor, 240 volt compressor. Then you have another switch which controls the different capacitors. There's capacitors inside this box, and the higher the farad value of the capacitor, the more kick or jump start that it gets when it's connected and trying to help unlock a stuck compressor. So just watch him start it up for a second.
So what we gotta do is turn it off, hit 300, and we'll go forward, and then start. And it started. Sounded like it had a little bit of rougher time starting that time.
For some reason I just lost internet on that video, so I'm just going to close that video out for a second, and I'm not going to do this hermetic analyzer video here, but what I do want to talk about is that they have those refrigerator 3-in-1, or what they call hard start kits. I'll see if I can find this one here.
What's up, YouTubers? Johnny DIY here. Today I'm going to be showing you guys how to fix your fridge and put a 3-in-1 relay starter in. If you guys are new to this channel, please consider subscribing. I do a lot of these how-to household and...
I am having internet problems for playing this video, so let me just talk for a second. You guys can hear me, right? Instead of playing these videos, something's happened to the internet in my my home. But the 3-in-1 kit is good, or the universal. The RCO 410, RCO stands for relay, capacitor, and overload. If you had a compressor that wasn't working on a refrigerator, and we're not talking about ones with the inverter boards, we're talking one that has a relay and overload on it, you could take one of these devices and install it on the compressor and see if it gets the compressor going. So they usually have larger capacitors in there. And it's a good way if you went to someone's home and a compressor wasn't running and you were like, well, ma'am, I think you need a new compressor, but what if it's just a bad relay or overload? For a while, Whirlpool had these compressors that the relays were going bad left and right. And sometimes you might not have the same exact relay, and it's very important to have the correct relay or the compressor is going to burn out or not work right. So you could use this to test a compressor, and what we do in class is there's 5 wires on there. 2 of them are line 1 and neutral, and the other 3 is red, white, and black, and they'll go, red goes to the run winding, white goes to the start winding, and black goes to the common. I have a video where I show how to test a compressor and install one of these on a compressor, so you could watch that video on the YouTube channel. But I kept one of those in my truck with a test cord on it, so if the customer's refrigerator did not run, I'd connect one of these to the compressor and see if I get the compressor running. If I did, I sometimes would leave that on the customer's compressor and try to come back with a relay and overload. But if the compressor is still hard starting, most likely the compressor is bad. So this is a quick way to tell whether you have a bad relay and overload or a bad compressor. I don't always recommend leaving them on compressors. I've had I would say a 60-40, 80-20% where the compressor ran, and then a month later or 2 months later, the customer calls me back and says, my refrigerator's not cooling again and the compressor burned out. It could be that the compressor was trying to run for who knows how long with a bad relay till I came out and tested it, so the windings started getting damaged by overheating and having excessive current draw trying to run that compressor before I got to it. Or the 3-in-1 kit may not be the right size for the compressor it was connected to. If you look at these 3-in-1 kits, they're rated on horsepower, and there's like 1/8, 1/3, 1/4, and then they got some high as half horsepower. You don't want to put a half horsepower 3-in-1 kit on a little refrigerator compressor. It may only be 1/8 or 1/4 horse. So if you have the wrong one, it's almost like putting the wrong relay on a compressor. So I'm not going to play this video only because for some reason I don't think my internet's going to handle it today. I'm just going to see if I can advance to where he's connecting it. So this one here is a special 3-in-1 because these 2 wires right here, I know you can't really see it too clearly, I'm press play, are extra plugs, and those are designed to add a capacitor, because some refrigerators and the relays down here in gray and the overload somewhere, but the existing refrigerator may have an additional capacitor which you would connect to these 2 plugs right here.
I have a couple little connectors right here that we're going to plug into our capacitor leads right here, the male ends. So we'll just go ahead and plug these into the female ends.
Now remember, this device, that round tubular piece at the bottom of this hard start kit or this 3-in-1 kit, is a capacitor already, so you're doubling the capacitor power already.
On the red and white one, it doesn't matter which one goes to which lead. So these are kind of daisy chained wires, you'll see. So then it's got 2 more leads, and the black one, these are going to go to our compressor. There is 3 prongs on the compressor, so the black one is going to go onto the bottom one that is by itself. That is the ground.
No, that's not ground, that's a common terminal.
On. This red one is going to go to the one on the left, towards the back. And the white one is going to go on the one closest to us. Just push all those on there.
Okay, there is a picture on the kit that shows wiring. Don't always 100% go by that picture, which says red is the run winding, white is the start winding, and black is common, not ground. I always recommend before you connect that to a compressor is by ohming that compressor out. The run winding is always the lowest resistance. The start is always higher than the run winding. And he was right. The one pin by itself is usually the common pin. So if you can look at the three and see one on the top and two on the bottom, or one on the bottom, two at the top, if you see the one by itself, almost assume that that's the common one, and put your meter on that common one and touch the other two. Whichever is the lowest, you put your red one. And then the higher of the other one, which is the higher one, you put the white, and then you put the black on that common terminal. So I didn't like the fact that he said ground, and he is telling you put it in the back and the front. He may be wiring it properly, but he didn't test it with the meter. So what if that compressor was shorted or grounded? You want to take an ohm meter and make that test real quick, because otherwise you're going to damage your hard start kit here.
And these two remaining black wires are going to go into the two wires we unplugged from our start relay, our original ones, and we're going to be connecting.
Tell you, my internet is really having a hard time here, guys. Sorry about that.
These with these wire nuts that came with it.
Okay, couple things. So that wire he has in his hand right here, and this other wire, they would be coming from the refrigerator controls, and they would plug into the relay and overload that was already on the compressor. Don't cut them off, because if all you need is a relay or an overload, then you have to put terminals back on the end of that. So what I do is I would just stick the wires right in the end of the terminals from your 3-in-1 and see if the refrigerator works before you start cutting the wires out. Maybe you have a bad compressor, and if that's the case, some compressors come with new relays and overloads, we call the electricals. Or if I had to replace a compressor and the electricals didn't come with it, I would order the right relay and overload for it, not leave a hard start kit on there.
So we'll just go ahead and snip the original wires, and we're going to strip them back a little so we have some copper wire.
I'm going to fast forward just a little bit.
The other one, the other black wire, puts them together.
Boy, my internet's real bad today.
And put our wire nut on. And that is it. Now we can plug our fridge in and test it. Alright, sounds like it is working. Alright, great. Now we know the fridge is working again, so we can go ahead and unplug it again. And now
here he is hardwiring that into the wiring of the refrigerator, which means the timer and thermostat or the control board is sending power to this and telling the compressor to run. That's why I would take those two wires that he had here and connect it to the refrigerator wires. I would already have a power cord from an old appliance, or go to Home Depot, Lowe's, buy yourself a test cord or cheap extension cord, cut the female end off that cord and wire nut it to one of these 3-in-1s and keep it on your truck. And then you could just plug it into that compressor and then just plug in the test cord. All you're running is the compressor. You can see if the compressor is good and the condenser and evaporator are getting warm and cold like they're supposed to. Then you can permanently wire it in the fridge. If you cut these wires of the refrigerator and then you find out the compressor still doesn't run after using one of these kits, now you got to change the compressor. You don't want to leave this hard start kit on a new compressor. You want to use the right relay and overload. So making these changes to the wiring of the refrigerator, you would only do it if you're going to permanently leave one of these installed to it.
We are going to put the relay and capacitor in, and you can go ahead and use a zip tie just to tie it to something on the side so it doesn't get jostled around. But you want to make sure your fridge is unplugged so you don't get electrocuted when you're fiddling with these wires. Then you put.
Alright, I'm going to end this today